Hello, my friends. This is an introductory, kind of a one day little intro into thermodynamics. And thermodynamics has to do a lot with transfers of energy and how you do that, how you transfer energy to quote unquote a system. And that system is typically assumed to be an ideal gas. All right. So what's great about this is you've done this in chemistry. It should look pretty familiar. Whoops, should look pretty familiar, but we get to review it again this year. So, by definition, ideal gases are gases that behave according to certain laws or equations that relate three things: pressure, volume, and temperature. All right, we say that those are three quantities that can define the state of a system. All right, pressure, we know we're gonna use capital V and measure in pascals. Volume is capital V, measure in cubic meters. Temperature is T, we're gonna measure it in kelvins. Okay, so there are three graphs that we ought to be comfortable with, and they relate these three things. So I'll do let's do, say, pressure and temperature. All right, that's one where, well, it just looks like this. It's a linear graph, which means that, well, the higher the temperature of a gas, really that means the faster its particles go, okay? And, I should probably put that in here because by definition, we say that temperature is the measure of the average kinetic energy of molecules in a system. So we'll get to that a bunch more, but temperature is really about how fast particles are moving. All right, and the faster they move, the more force they exert when they collide with the walls of a container, and therefore the larger the pressure that gas is under when it's in a container. Okay? This also says that pressure and temperature are directly related, or we can say this: P1 over T1 is P2 over T2. That's probably a law of someone's. I don't remember the names of them. Well, then we can do pressure and volume. Well, this one looks like this. And it says that, well, the more space you give a gas to occupy, right, if this is big, well, the less pressure the gas will be under. And that's because, that's because the particles, when they move around, will literally, if there's more volume to occupy, they have to literally travel farther between collisions with the walls of a container. And if they travel farther, it takes longer. And if it takes longer, well, the container will really, you can almost imagine the container trying to collapse, but it doesn't because of the collisions between the molecules of the gas and the walls of the container. So if those collisions are less frequent, well, then there's less pressure. Okay, but what this does say is, notice that, well, it says that pressure and volume are inversely proportional. Okay, so, notice big pressure, small volume, small pressure, big volume. Okay, so small times a small times a big can be equal to a big times a small, right? Now the last one is we can relate volume and temperature, and that looks something like this. It's a direct relationship, so we can say that V1 over T1 is V2 over T2. And, well, what we can do with this is really say if we trace this all the way back to here, there's some temperature at which a gas occupies 0 volume, right? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0 volume. Here's 0 volume. So at this temperature right here, this is T in kelvins equals 0. All right? Absolute 0. All right, that's defined to be a temperature at which a gas occupies 0 volume. And that's because if temperature is actually absolute 0, molecules have 0 kinetic energy. They don't move at all. There are no collisions between molecules and the walls of a container, and therefore the container doesn't occupy, or the gas doesn't occupy any volume at all. Okay? Now, combining these three things, these three equations, 1, 2, 3, well, we can get, well, what's called the combined gas law. We can boil these all into this one. We can say that P1 V1 over T1 is P2 V2 over T2. That's called the combined gas law. And what it also says is that this quantity, P times V divided by T, is always the same. And so if we say that P V over T is a constant, well, then we can say that PV is a constant times T, or we can say that PV, where do I write this? I'm going to write it over here. So keep this combined gas law. Keep that. You'll use that. But we also get this, what's called the equation of state, which is that PV equals NRT, or PV equals NKT, right? The constant being, well, one of those, little n times big R, or big N times K. Well, little n is defined to be, in that case, the number of moles of gas, and big N is defined to be the number of particles of gas. And then the two other things, the R and the K are constants. All right, R is called the universal gas constant, and it is 8.31 joules per mole Kelvin. K is called Boltzmann's constant, and that's 1.38 times 10 to the negative 23rd joules per Kelvin. All right, you do not have to memorize those. You do have to know when to use which one, but there they are. I think that's right, 10 to the negative 23rd. Yeah, it's right. Okay? So 3 equations already. I'll rewrite the combined gas law. Whoops, 1 and 2 there. Okay? Those are our 3 equations so far. Now, the mole, right? We all know what a mole is. I think maybe you don't. The definition of a mole is, by definition, it's the amount of substance in a system which has as many parts as there are in 12 grams of carbon-12. So carbon-12, our most abundant element, okay? And therefore, lots of stuff is based on carbon-12. All right, a mole is defined to be this, that many elementary particles as there are in 12 grams of carbon-12. Well, how many is that? Well, it's this many. You've heard this. Particles. Right, so we usually say that. That's like a little conversion we can use. Okay, and notice, if we say that there are 8.31 joules per mole Kelvin, right? And then, let's see, there are, I'm using this right here, in 1 mole, there are 6.02 times 10 to the 23rd particles. Well, we multiply those together, and what do you get? You get 1.38 times 10 to the negative 23rd joules per Kelvin. Really joules per particle Kelvin, but a particle is just a thing, not really a unit. All right, so that's how, notice this is R and this is K. Same thing, just in different units. Okay? Okay, here's a question about a hot air balloon. There's our volume, there's our pressure, there's our temperature, what's the number of gas molecules. So that is an equation of state problem, and we're going to use the NKT, right? Number of molecules. We're looking for big N. PV over KT. All right? So let's see, pressure, 101,000, right? You got to use it in pascals. 101,000 times volume 1.13E4 divided by parentheses K 1.38 E negative 23 times temperature 291. I get N is 2.84 times 10 to the 29th particles. How many moles is that? Let's see. Well, we can say that in 1 mole there are 6.02 times 10 to the 23rd particles. So divide 6.02 E23. And that's still a hefty 4.72 times 10 to the 5th moles. Fair enough? It's okay? It's okay. Next. Now, kinetic theory. I don't know if you talk about this in chemistry or not, but kinetic theory is the way that we do things like explain, we being physicists, explain things like volume and pressure. All right? And it's, again, because objects, well, gases are made of objects. Those objects move around, and when they do, they bump into walls of containers. And those bumpings exert forces and therefore impulses to the particles and to the walls of the container, especially walls of the container that are able to move, like a balloon, right? Like where typically the balloon would be, because of its elasticity, would be in as small size as it can be. Well, the bumping of the air into those walls pushes the walls out while the walls are trying to pull themselves in. Okay, some assumptions. Yeah. Blah, blah, blah. Okay. So, fine. Sample A, there's sample A. So this is a piston, right? This thing here is a piston that can slide up and down in this cylinder. Okay? And, literally what we're saying is this one that comes up here bounces off of there. The object gets pushed this way, so therefore the piston gets pushed this way with the same force. All right, and every time it gets pushed upward, the piston, you can even imagine it sort of bounces up like this and wants to come back down. All right? Now, how high does it bounce up from each one of those collisions? Not very high. The impulse is very small, but the collisions, you got to imagine there are tons of them, and they happen at a pretty high frequency. Okay? So, in a case like this, let's compare a couple of samples of gas. And one of our biggest what do you call it? I don't know, targets or one of the things that's going to help us the most is to, in a lot of cases, identify what quantity is constant. Either in a certain process, we'll get into thermodynamic processes pretty soon, or in this case, just comparing two samples of gas. Well, they have a constant volume, the same exact volume, right? The size of the container is the same. We're going to fill in some blanks here. All right, particles in this sample, sample B, have, well, notice, twice the average kinetic energy of sample A. The volume is the same. So by increasing the temperature, and again, remember, temperature is a measure of the average kinetic energy. So this says that really, if this has a temperature, well, let's go down here. Temperature B really has to be twice that of temperature A. If the molecules have twice the kinetic energy, then that must mean that the gas is at twice the temperature. Well, those are the same, right? Saying the same thing here. By increasing the temperature, let's see, pressure it exerts on the piston, well, increases. Right? Kinetic theory says now that these things are going twice as fast, they will have twice the impulse when they do one of those bounces, and that means that there's twice the force exerted. And if there's twice the force per unit area, there must be twice the pressure. So that means we can support a mass of 2m. All right, so we would say, well, now we can hold up a mass here that we call 2m instead of just n. We can also look at this as an ideal or as a combined gas law. P1 V1 over T1 is P2 V2 over T2. Right? In this case, the volumes are the same. If the T2, well, how about this? A, B, B. If, let's see, we got pressure A, temperature A. Well, temperature B is 2 temperature A. That's what we said, right? That means our temperature A's go away. Well, we must have to have a 2 pressure A up here to make, yeah, this is 1 and this is now 1, right? So pressure B has to be twice pressure A. And that means we can hold up twice as much mass. Fair enough? Okay. Let's look at another one. How many of these are there? Come on. There's that one, there's this one. All right, I'll do one more with you and leave the rest to you. So in this case, what do we have? What's constant? Look around, what do you see? What's constant? Right. That means temperature is constant. The particles in this sample of gas have the same average kinetic energy. By decreasing the volume, the pressure it exerts must do what? Well, we can kind of look here. That's the same. The volume of C, well, I tried to make it as close as I can to a half. All right, well, so two ways to think about it. One, there's got to be, if the volume is smaller, you know, that literally the time it takes this particle here to say go up here and come back down there and go up here and come back down there is now half as much as it would take for this thing to do this. So the collisions can happen twice as often. And even though they exert the same force per collision, the collisions happen twice as often. So the pressure it exerts on the piston will increase. And therefore, if they're going, well, if it's half the volume, the collisions will happen twice as often. Now we hold up again 2m because the pressure is twice as big. All right, again, we can do this as an ideal gas or a combined gas law. A, pressure C, volume C, temperature C. Temperatures are the same. We get pressure A, volume A is pressure C times 1/2 volume A. Right? Get rid of the volume A's. And this says that pressure C is 2 pressure A. Okay? Try this one, and then try these. All right, so you're going to base everything on this. This is kind of your baseline. All right, here we're looking for the temperature. Here I tell you some stuff. Same temperature, twice the volume. How much mass? You know, we're kind of looking for pressure here. Here I tell you the volume. I tell you how much mass. We're looking for temperature. Here the volume is how big? I don't know. Well, I tell you how the temperature of the gas. I tell you the mass, or really the pressure it exerts. Okay? So when I say, you know, this volume, this is volume V. Right? If they have kinetic energy E, that means they're at temperature T. And if that's the case, this gas exerts a pressure P. Or really a pressure P is linked to being able to hold up a mass M. Okay, folks? So let's see. This we'll look at for, yeah, just whenever I have it on the calendar. Okay? Okay, folks. See you soon. Yeah. Oh, yeah. We'll get to this stuff. Don't worry about it.